We'll start section B. Question number 15. This question is about hydrated salts. The enthalpy change for the conversion of anhydrous copper to sulfate to the hydrated form can be found using Hess's law. A student carried out experiments to determine the value of enthalpy change. Then known masses of anhydrous and hydrated copper to sulfate were dissolved separately in water in insulated containers, and the temperature changes measured. Okay, we'll go through the table. Here, hydrated copper sulfate 12.5 grams, anhydrous one 8 grams. Then volume of water added 45.5 and 50. And the temperature changes have been given. Now here don't get misled. Here temperature change minus means enthalpy change is plus. Temperature change as plus means enthalpy change is minus. We'll see why. Here in the first one, when hydrated copper sulfate dissolves in water, the overall enthalpy change is minus 3 degrees Celsius. This means there is a decrease in temperature. In order to decrease the temperature of the solution, the solute should absorb heat from the solution or the solvent to dissolve. Therefore, when energy is absorbed, the enthalpy change is plus. The second one, when anhydrous copper sulfate dissolves in water, enthalpy change is positive. Temperature change is positive. This means there is a rise in temperature. This shows that heat energy has been supplied to the solvent or the solution once copper sulfate dissolves. Heat energy is given out means it is exothermic. So first one is endothermic, second one is exothermic. Then for the first one, enthalpy change should be plus. For the second one, the enthalpy change should be minus. Then Roman number 1, state why different volumes of water are used in 2 experiments. Okay, here in the second para they say that a student carried out experiments. Then we have to read the mind of the student to find why he has used different volumes. But by using chemistry, we should guess why he has used different volumes. See the question again. State why different volumes of water are used in the 2 experiments. Just by looking at the table, here you can see 12.5 to 8 is the difference from hydrated to anhydrous. Then in order to compensate the decrease in mass from hydrated to anhydrous, the volume of water or the mass of water added has been increased, where the total mass of the system, that is the final total mass of the solution system, has been kept constant or equal in both the cases. Then state why different volumes of water are used. Here just by looking at the table we can say, in order to make the total mass constant, or in order to make the total mass equal in both the cases. Here when we go through the given data in under Roman number 2, they say that assume heat capacity of the solution 4.2 joules per gram per Celsius, that is the solution. Again, density of solution is 1 gram per centimeter cube. Here density of the solution should be assumed to be 1 gram per centimeter cube. So if the total mass is X, then according to the given assumptions, the total volume should be the same as that. Therefore, we can say that in both cases the total volume has been kept constant or equal in both the cases. So here answer, you have to say the mass of or the difference in mass between hydrated and anhydrous copper sulfate is 4.5. In order to compensate that difference, extra 4.5 grams of water has been added to the anhydrous copper sulfate to make the final mass of each solution the same, followed by the final volume of each solution is kept constant or equal. That is the justification. Now or else if you are familiar with the relative formula masses of these two, then being teachers we can remember them. Here copper sulfate, here 160, because once the rounded off values are used, 16 into 4 plus 32 plus 64, normally we use 64, then altogether 160. In the second case, 160 plus 5 water, 18 into 5, 90, 160 plus 90, 250. So if 250 grams is taken, 1 mole, then 25 grams, 0.1 moles, 12.5, 0.05 moles. Second one, 160 means 1 mole, then 16 grams means 0.1 mole, then 8 grams means 0.05 moles. So the number of moles of hydrated and anhydrous copper sulfate should be the same based on the rounded off values. There may be a slight difference based on the relative atomic masses given in your periodic table. According to them, copper is not 63.5 and sulfur is not exactly 32, that is 32.1, oxygen 16, hydrogen 1. Okay, there is a slight difference. Anyway, when we take the rounded off values, we can say the same number of moles of copper anhydrous and hydrated copper sulfate have been used. Therefore, when the same number of moles are used in each case, the additional 4.5 grams of hydrated copper sulfate should be responsible for the extra water, that is the water of crystallization. So that 4.5 grams of water has been compensated when 4.5 extra water has been added to the anhydrous copper sulfate. Okay, we'll go through the mark scheme also. In the mark scheme, they say the hydrated crystals already have a certain amount. They say again 4.5 grams. We'll see whether it is 4.5 grams. Here, when you use the exact values, exact relative atomic masses given in your periodic table, according to them, copper is 63.5 plus sulfur is 32.1 plus, then oxygen is 16 into 4, 64. So the relative formula mass of anhydrous copper sulfate is 159.6. 159.6 is the relative formula mass of copper sulfate anhydrous. Then hydrated one, plus 5 water, then 18 into 5, that is 90. Then plus 90 means 249.6. So when they have used 12.5 grams of hydrated copper sulfate, the number of moles found here should be 12.5 divided by 249.6. Then the answer is 0.05008. Here the answer is 0.05008, 0128. Okay. Then we'll take the number of moles of the second one. Here 8 divided by the relative formula mass here is 159.6 divided by 159.6 equals 0.05012. 0.0501253. There is a slight difference in the number of moles. Therefore, in the first case, if we take the exact value 0.05008 moles are there, then number of moles of water should be that into 5. Then number of moles is 0.05008 into 5, then 0.2504. That into 18 is the mass of water. Then 4.5072. 4.5072. So it's not exactly a 4.5. There is a slight difference, but don't worry about that. Here exact volumes are not essential to do this experiment. We'll discuss the theory behind that. Here heat change equals ms delta T. Then here, according to the given data, being students, you should know that they say that density of the solution is 1 gram per centimeter cube. Then if the total mass of water is 50 grams, actually we have to consider the specific heat capacity of water here. Normally we don't take into account the specific heat capacity of solutes, because the solvent water has a very high specific heat capacity, significantly high specific heat capacity due to the high occurrence of hydrogen bonds, strong hydrogen bonds. Okay, then here according to the density equals 1 gram per centimeter cube, then once the total volume is 50 cm cube, there should be 50 grams. But really this is not the real way of preparing 50 cm cube of copper sulfate solution. If you have added 50 cm cube of water to 8 grams of copper sulfate, the spaces between water molecules are occupied by copper 2 plus and sulfate ions, thereby there may be a slight expansion of the solution. Therefore the density is not exactly 1 gram per centimeter cube. Then first you have to dissolve copper sulfate solid in a volume which is well below 50 cm cube. Then homogenize the solution, followed by slowly add deionized water until the total volume of the solution becomes 50 cm cube while it is being homogenized while adding water. But here the student has directly added 50 grams of water to 8 grams of copper sulfate, but even though the total mass is 58 grams, it's not 58 cm cube, neither 58 nor 50, it's very close to 50. Then don't bother about that. Here if you have added 50 grams of water, then really here mass is 50 grams. Specific heat capacity is according to them 4.2 joules per gram per Celsius into temperature change is 16 degrees Celsius. Therefore, if you change the masses of water added slightly different in each event, here the mass slightly changes means delta T will be changed slightly. We'll take here H equals ms delta T. Here specific heat capacity is assumed to be a constant in both the solutions. Then heat energy given out is directly proportional to mass into delta T. Suppose the student used slightly different masses of water in the two events. Suppose we'll take in the first event he used, we'll say 49 grams, in the second one 50 grams, like that. Still, if there is a decrease in mass of the solvent, then proportional to that there should be an increase in delta T. Then you may argue if there is a huge difference, still it should be correct. Now we'll say H directly proportional to M into delta T. We'll say in one event we use 50 grams of the solvent. In the second event we use just 5 grams instead of 50. Now if the mass has decreased tenfold, 10 times, delta T should increase 10 times. Then still theoretically you should gain the same heat change, but in a scientific experiment, other than the desired variable, all the other factors should be made the same, made constant as much as possible. Here imagine when the mass of water is 50 grams, we'll say delta T is just 1 gram. Then mass of water is 5 grams, then instead of 1 it should be 10 grams, like 10 degrees Celsius, like that. Here rise in temperature when the mass decreases tenfold, delta T also should increase tenfold. Then the heat loss to the surrounding will be different, and we'll say that the uncertainty of measuring is plus or minus 0.05 the temperature. Then if there are two readings into 2, then if the uncertainty is 0.1, then 0.1 divided by suppose here when the mass is 10 times less, the delta T is 10 times greater. When the delta T is 10 times greater, then here denominator becomes greater 10 times, then it is an advantage into 100%. Then percentage error, plus or minus percentage error, will be less when the temperature rise is greater. That is an advantage. But again there is a disadvantage. When the temperature is greater, there is a significant heat loss, greater heat loss. Therefore, we have to think of the compromise of these two. Then it is complicated. Therefore, in the scientific experiments, we have to keep the other factors the same as much as possible in practice. Therefore, here the student's attempt is fair. Here he tries to make the total volume the same in each event. Thereby, heat loss to the environment will be almost the same. Then the percentage uncertainties or the percentage error calculated will be almost the same in each case. Like that, he has attempted to make the other variables almost the same. Okay. Here's short and sweet answer is here the mass change is 4.5 of the hydrated to anhydrous. Then in order to compensate that mass, there is an increase in 4.5 grams of water added to the anhydrous copper sulfate. Thereby, final volume of the solution is kept the same for both hydrated and anhydrous state. Then Roman number 2, calculate the enthalpy change of solution for the anhydrous copper sulfate. Then you have to use ms delta T. Here 50 cm cube or 50 grams M50 into S according to them 4.2 into delta T 16, that is MST, delta T that is given in joules. Then answer divided by 1000 comes in kilojoules. This heat energy is given for a specific number of moles. We'll see the number of moles. Then this divided by the number of moles. Here number of moles is 8 grams divided by it's not 160, 159.6. Okay, then the answer is 67.032. 67.032 is the heat change per mole. Then we have to think of the sign here. For the second one, temperature change is plus 16. If the temperature change is plus 16, that means heat energy has been liberated in the dissolution of copper sulfate. Then the enthalpy change, it is an exothermic one, then the enthalpy change should be a negative one. Then you have to put a negative sign in front of that. Then minus 67.032 kilojoules per mole is the final answer. Okay, we'll move to the next one. Roman number 3, complete the Hayes cycle by adding 2 arrowheads here. Here in the first one, anhydrous copper sulfate to hydrated copper, aqueous copper sulfate. We'll take Here anhydrous copper, starting point is anhydrous copper sulfate, then 5 water, then hydrated, followed by excess water should be there, then it is copper sulfate aqueous. Delta H solution of copper sulfate, anhydrous copper sulfate. The second one, delta H solution of hydrated copper sulfate. Then the arrowhead should move downwards. Then calculate the value for the enthalpy change for the conversion of anhydrous salt to hydrated salt. Here anhydrous salt to hydrated salt is the arrow indicated from left to right here. Then according to Hess's law, this value, you have to think of the vector quantities here. You have to consider the sign here. Here when you change the direction, algebraic values should be taken. Here delta H, second one is minus, then it should be plus. So we'll see here according to the given chart. So first one is once the enthalpy change of solution of hydrated copper sulfate is plus 12.5, 12.6. Then when you reverse the arrow, it should be minus. So here it should be minus 12.6. Then downward arrow, here we found it earlier, it was 67 point minus 67.032. Then count them, 67.032 plus 12.6, together 79.632 kilojoules per mole is the final answer. Then see whether it is plus or minus. From anhydrous copper sulfate to aqueous copper sulfate minus, again hydrated copper sulfate to copper sulfate aqueous plus, but when you reverse it, that is also minus. Then altogether this is an exothermic reaction. Therefore in front of the answer you have to put minus value. Then we'll see the number of significant figures that has to be given. They haven't specified any number of significant figures here. Then we'll round it off as minus 79.6 kilojoules per mole. Okay, that's the answer for that. Then part B, the hydration of anhydrous copper sulfate is reversible. The hydration of anhydrous copper sulfate is reversible. From O levels you know that we use copper sulfate, anhydrous copper sulfate to detect the availability of water vapor in the atmosphere. So once anhydrous copper sulfate slowly absorbs water vapor, it turns copper sulfate pentahydrate, which is blue in color. Then white to blue is the color change. The forward reaction is exothermic. They say that the forward reaction is exothermic. The temperature changes for both the forward and the reverse reactions are difficult to measure. Then I think from your O levels you know that it is difficult to measure directly. Suggest a reason in each case. We'll see why it is difficult to measure. Then forward reaction. Now how to add water to copper sulfate to make it copper sulfate pentahydrate. We'll take an example. Suppose you are going to distribute 1000 lunch packets. Suppose there is a ground here. There are 1000 beggars in the ground, and you are going to, a single person is going to distribute 1000 lunch packets to 1000 beggars who are about to die due to the lack of any food. Then you are going to distribute equally, but forcefully they will grab your lunch packets. Then we'll say the first beggar grabs 5 lunch packets, second one 4, 6, different values. Then finally when you move around 100 beggars, now all the lunch packets are now over. Then the other will gain nothing. So you can't equally distribute lunch packets among them. Similarly, even though you be as a chemist, suppose you are going to calculate the exact masses of copper sulfate and water that should be added proportionally to which suits for copper sulfate pentahydrate. We'll say copper sulfate is 160 grams. Then 160 grams of copper sulfate plus 5 water, 18 into 5, 90 grams. Then you are going to mix 160 grams of anhydrous copper sulfate and 90 grams of water. Then you may expect to form copper sulfate pentahydrate. But when you mix them, some copper sulfate, some particular part, microscopic part of copper sulfate will gain more water. It will end up as a solution. Sometimes in some parts the lattice may be unable to gain 5 because all 5 are not in the same plane. 4 are in one plane, square plane. One is in between copper 2 plus and sulfate. There is a different arrangement there. Then they will gain different amounts. Then sometimes a solution will be formed, sometimes still it remains as anhydrous. That means even though you have used the correct proportions of anhydrous copper sulfate and water, you will not end up it as exactly copper sulfate pentahydrate. Therefore it is very difficult. You just imagine that example. You can't evenly distribute 1000 lunch packets over 1000 beggars if an individual does that job. The others will cover him, then he will be crowded, or all will be pulled away by strong ones. Okay, then one reason is we can't exactly end up as copper sulfate pentahydrate. In some cases, in some areas of the solution or the crystal, there will be in some places of the crystal it will end up as a solution. In some places still it remains as anhydrous copper sulfate. It is not distributed evenly. Then one problem is that. Then the other one, now you go through your values obtained here. The once anhydrous copper sulfate ends up as a copper sulfate solution, you got minus 79.6 kilojoules per mole as the enthalpy change. It's highly exothermic. Due to the heat energy given out, even though you start at we'll say at you start at 25 degrees Celsius, but when it bonds with water, heat energy will be given out. Then sometimes a significant fraction of water will be vaporized. Then latent heat of vaporization will be absorbed by this solvent. Therefore, you can't measure the exact temperature change, because you are going to measure the temperature change, delta T, in this experiment. So one thing is uneven distribution of water in different places of the crystal. The other one is some water will be vaporized. The other thing is, now you know that when you go to a doctor, you think how the doctor measures your body temperature. Does he put the keep the bulb of the thermometer on the skin of your hand? No. There should be a well surrounded area. Therefore, in order to measure the temperature in a scientific way, there should be a better thermal distribution within the system. But in a solid, the thermal distribution from one place to another is very poor. Therefore, you have to keep the thermometer bulb at, we'll say, 10 places, followed by you have to take the average. Still it will not be because if you are going to measure the temperature at 10 places, you have to spend a lot of time. Within that time period, there may be a huge heat loss as a percentage. Therefore, measuring the temperature delta T of a solid is very much difficult. It's not practically, actually not impossible, but you have to struggle more. Okay, then these are the main points here. Then reverse one. In the reverse direction, that is from hydrated copper sulfate to anhydrous copper sulfate. Here you have to remove the trapped water in the hydrated copper sulfate. You know that the reverse reaction is endothermic. Copper sulfate to copper sulfate dot 5H2O is exothermic. Then the reverse one is endothermic. If it is endothermic, practically you have to expect a decrease in temperature. Again, you see, the reverse reaction is endothermic. If it is endothermic, in an experiment, you expect a decrease in temperature. But you have to think of a kinetic factor here. These water molecules have bonded strongly to copper 2 plus ions. Out of 5 water, 4 are bonded very much strongly through dative covalent bonds. Here, removal of these 5 water molecules need a significantly high activation energy. In order to achieve that activation energy, copper sulfate pentahydrate should be heated strongly. I think you have that experience in your O levels. In the O level practicals, we have heated and shown the hydrated copper sulfate until the blue color turns to white. We have to apply the Bunsen flame around 2-3 minutes, over 2-3 minutes to make it white. You know that Bunsen burner gives a flame with around 600 to or 700 degrees Celsius based on the combustion. Then even at that high temperatures, we have to heat it for a significantly longer time period to make the blue solid to white, hydrated to anhydrous. That means it's highly endothermic. Even though it is endothermic, in order to overcome the activation energy, we have to heat it. Now again see, since the backward reaction is endothermic, theoretically you should expect a decrease in temperature. In the reverse reaction, you expect a negative one, that means a decrease in temperature. That is because of the endothermic reaction. But practically we supply heat. When we supply heat, there is an increase in temperature. Then the respective calculation will be very much complicated. Then you have to think the maximum temperature achieved if provided that the backward reaction is not taking place. Suppose you apply X kilojoules over the time period by using the Bunsen flame. Out of X, we'll say Y kilojoule is absorbed for the removal of water. Then X minus Y is the apparent temperature rise. See again, you supply X kilojoules of heat to occur in order to make the backward reaction. Out of X, Y kilojoule is absorbed to remove the water molecules. Then X minus Y will be the apparent heat energy change. That means based on that, proportionally, you will observe an apparent temperature rise. But it becomes a very much complicated calculation being a student. But at this case, we have to pay gratitude to this Hayes law. According to the Hayes law, we shouldn't bother about such complicated calculations. We can apply separate values for the delta H solution of hydrated one and anhydrous one. Through that, we can find the enthalpy change when the hydrated one becomes anhydrous or anhydrous one becomes hydrated. Okay, then here practically we have to heat, then there is an increase in temperature, but theoretically we expect a decrease in temperature. One thing is that. The other thing is again just like the above one, the temperature of a solid is difficult to be measured. It is difficult to measure the temperature change of a solid. You have to take the average there. Then these are the main ones. Then other than that, if you strongly heat copper sulfate pentahydrate, CuSO4.5H2O is heated, then gradually water molecules will be eliminated. We'll say finally it becomes just CuSO4. Even thereafter, under strong heating, it will undergo further decomposition. We'll say here copper is at +2, sulfate is at +6, oxygen is at -2. We'll say that copper sulfate decomposes into sulfur dioxide. Then it goes from +6 to +4. That's a reduction if there is a reduction, there must be an oxidation. Then copper is at +2, highest possible oxidation state practically. Then -2 is oxygen is at -2. So if sulfur dioxide evolves, that's a reduction, then the oxidation should be, and O atom should be formed proportionally, but O atoms are unstable. Then if 2 sulfur dioxide evolve, 4 electrons accompanied with that, then here O2 molecule can escape. Then if there are 2 sulfur dioxide, there should be 2 copper sulfate. Then out of 8 oxides, here 6 oxides, then CuO, 2 copper oxide. Here if copper sulfate decomposes in this way, the entropy of the system increases. Here sulfur dioxide gas, O2 gas evolve, strong lattice copper oxide has been formed. It is thermodynamically feasible provided that sufficient energy has been supplied here. So if you strongly heat copper sulfate, it may undergo decomposition. Normally copper sulfate does not undergo decomposition, it's a stable one, but under high temperatures the delta G will be negative. Here copper, it is favorable, thermodynamically favorable at high temperatures, very high temperatures. Then it may be copper oxide, sulfur dioxide and oxygen. You may suggest different decompositions. Anyway, copper sulfate may decompose in this way also, copper oxide, sulfur dioxide and oxygen. So such difficulties are there in the reverse direction also. You have to mention these things here. Describe the processes that occur when solid copper 2 sulfate dissolves in water. When solid copper sulfate, here in solid copper sulfate may be hydrated or anhydrous. Here strong attractions are there, electrostatic attractions are there in the ionic bonding. When water molecules approach slowly, the ionic lattice will be broken. These are simultaneous occurrences, just like I think you can remember SN2 reaction mechanism of, we'll say, halogenoalkanes. We'll take a bromoalkane, primary bromoalkane. Then when sodium hydroxide is added, hydroxide ion approaches the Br bonded carbon simultaneously. This existing CBr bond slowly breaks like that. Here when water molecules approach copper 2 plus and sulfate 2 minus, so slowly the existing ionic attractions will be weakened, and simultaneously ion dipole interactions will be formed by using oppositely charged ends of water. Then these are simultaneous occurrences, but in the exam, the art of answering the question is describe the processes. Then you have to give 2 separate processes here. One is breaking the ionic lattice. You have to break the ionic lattice, one thing. Thereafter respective ions are hydrated by using ion dipole interactions. Even though we write it as 2 separate events, actually they do not occur one after the other. The copper sulfate is not crazy to be broken itself. before reaching water. Both these events should occur simultaneously. Then in the exam, in order to make it clear, you have to say first the ionic lattice is broken to separate the ions, followed by the respective ions are hydrated with ion dipole interactions. Okay, part D. Hydrates of sodium carbonate may be represented by the formula sodium carbonate dot XH2O. The value of X can be found by making up a solution of sodium carbonate and titrating this with a solution of hydrochloric acid of known concentration. A known mass of sodium carbonate XH2O was dissolved in water, made up to the mark in a 250 cm3 volumetric flask and mixed thoroughly. 25 cm3 portions of the solution were titrated with 0.09 m hydrochloric acid using methyl orange as the indicator. The mean titer is 25.6 cm3. Equation has been given. Equation has been given by protonating the carbonate ion with 2H pluses. You have to obey to that. In unit 4 you will understand that methyl orange changes its color from around 3.1, we'll say 3.1 to 4.4. Then above 4.4 it's yellow in color. Below 3.1 it's red in color. In between it's orange in color. So here the solution 25 portions of it has been titrated with hydrochloric acid. Then when you add hydrochloric acid, here carbonate is first undergoes first protonation to form bicarbonate. Then the pH decreases, but still the indicator is not sensitive for that because its pH working pH range is well below 7. Then the second protonation takes place, then carbonic acid followed by it decomposes to form H2O CO2. Thereafter it will gradually change to orange. Therefore when the indicator indicates the color change from yellow to orange, both the protonations have taken place. Therefore you have to use this equation for that 1:2 ratio. Calculate the amount in moles of sodium carbonate in 250 cm3 of the solution. Here the mean titer is 25.6. Here we'll take the calculator. Here concentration is 0.09, that into here 25.6 cm3 has been used for that 25. Then 250 for the whole solution, it should be 256, means 0.256. Then into 0.256, that's the number of moles of total number of moles of HCl required to titrate with the whole 250 cm3. That divided by 2 is the number of moles of sodium carbonate. Then sodium carbonate is 0.01152 is the moles of sodium carbonate. Then they have used asking the calculate the number of moles. Yes, that's the answer. Then so yeah, we have reached the answer 0.1152. But in the exam you have to follow the sequential order here. Second one, 250 cm3 of solution was prepared by dissolving 3.29 grams of sodium carbonate XH2O Use this mass and your answer to D1 to determine the value of X. Give an answer to appropriate number of significant figures. Okay. Then so this much of moles is represented by 3.29. Then 3.29 divided by this is the molar mass. Then 3.29 divided by 0.01152, 285.5902. Okay, this is the molar mass. Here this comes in grams, this comes in moles, then grams per mole. Then you know that sodium carbonate itself is 16 into 3, 48 plus 12, 60, 23 into 2, 46, altogether 106. Then subtract 106 here roughly 286. 286 minus 106 is here 180. So mass of water is 180. You know that the molar mass of water is 18. Therefore, there should be 10 water per 1 mole of sodium carbonate. Therefore, this is Na2CO3.10H2O. Then you have to write the steps here. So since this is part B, you write the respective steps. Number of moles of HCl used in the titration C into V, concentration 0.09 moles per dm cube into 25.6 divided by 1000, that is the number of moles of HCl. Then therefore N sodium carbonate present in the titration flask should be this answer divided by 2. Therefore N sodium carbonate in 250 cm cube equals this answer into 10. Like that you have to show the steps here. For the second one also you have to show the steps. Use this mass. Okay. Then here we have already calculated the number of moles here. Here N equals simple M over capital M. Here we know number of moles, we know mass, then unknown one is capital M, subject capital M. M equals mass divided by N, then mass has been given 3.29 grams divided by the number of moles. We found it earlier. This divided by this gives the molar mass of sodium carbonate XH2O. Then subtract the molar mass of sodium carbonate itself without considering water, that is 106. Then the remainder is water, you have to tell that. Then that quantity of water divided by 18 is the number of moles of water per 1 mole of sodium carbonate. Like that you have to, being a student, you have to write all. Then 16th question. This question is about trends in the periodic table. The boiling temperatures of some isoelectronic hydrates are shown here. Here carbon CH4 methane means 6 plus 4 10 electrons, ammonia 7 plus 3 10, water 8 plus 2 10, HF hydrogen fluoride 9 plus 1 10. So all of them have 10 electrons. Explain the difference in these boiling temperatures by considering all the intermolecular forces involved. Detailed description of the intermolecular forces involved are not required. Okay. Here These are simple molecular structures. Now, before writing an answer, you should have a proper plan of writing the answer. In order to have a proper plan, you should have well organized pieces of theory behind that. We'll see how to approach an answer here. There are no ionic lattices here. There are no giant covalent lattices here. All are simple molecular structures. Being simple molecules, we have to think of intermolecular attraction forces when we discuss about boiling temperatures. Here, when we take methane, only London dispersion forces are there, being nonpolar. Methane is nonpolar, therefore only London dispersion forces are there. Then others have London dispersion forces, PD attraction forces, hydrogen bonds, all are there. Then the lowest boiling point should be shown by methane, because the London dispersion forces are similar in strength, not identical. Their surface area is different, arrangements are different, anyway not identical, anyway similar. Being isoelectronic, all the four molecules should show similar strengths in London dispersion forces. But other than the London dispersion forces, ammonia, water, HF show hydrogen bonds as the key intermolecular attraction force here, because that is the strongest. We'll ignore PD attraction forces. Therefore, all three should show greater boiling points with compared to methane. Really, it's a 243, 73, 293 like that, but methane is 112 Kelvin. Then explain the difference in these boiling temperatures. We'll see how to do it. Here you have to say being, we'll say being simple molecular structures, the intermolecular strength of intermolecular attraction forces govern the change in boiling point or the boiling point as the first point, as an approach. Then you have to say only methane